Hello everyone, welcome to the first lab of prime time. In this lab I will focus on, I have an example RTL on which I will demonstrate the use of timing exceptions. Mostly we'll talk about false path, then we'll talk about case analysis, we'll see the use of virtual clocks in exceptions and so on. And then we'll look at some pre-layout timing reports. I'll try and point out the most important things that we should check for pre-layout before going to post-layout. So we talked about this example in the session, the last theory session. This is an example where it's a completely combinational logic. There's an adder. There's a select pin which selects which of the signals from A and B or C or D goes forward. The first output is E, the second output is F. So this output is E, this output is F, and if S is 0, the functionality says that if S is 0, A and C go forward, they get added together and the output goes to E. F is 0. If S is 1, then B plus D go on to F and E is 0. So I have written the RTL and synthesized it. So the RTL, let's look at the RTL first. Very simple. So this is the RTL where module name is example. Inputs, these are 4-bit inputs A, B, C, D. Input select, output E and F. Output is 1 bit higher to take care of the carry bit. And I have declared 2 wires, temp 0 and temp 1. Temp 0 and temp 1 represent the 2 muxes. So if cell is 1, it gets B, otherwise it gets A. If cell is temp 1 gets B, if cell is 1, otherwise it gets C. So these 2 temp wires represent the muxes. These muxes, the mux that selects between A and B and C and D. And then there's the adder here, the temporary sum, temp 0 plus temp 1. And then assign E based on if select is 1, then E gets 0, otherwise it gets the sum. If F gets the sum, if cell is 1, otherwise it gets 0. So these 2 assigned statements in the end, they represent this ANDing logic. So I have synthesized this now. This is a completely combination logic. You could choose one of the 2 strategies to constrain it. You could either set a max delay on this. So what I did was I set a max delay of 2 ns from all inputs to all outputs, and I synthesized it simply. You could also choose to declare virtual clocks and give input and output delays with respect to that virtual clock. It is exactly same as the max delay when it comes to synthesis. So I've written out the gate level netlist. We go to work. So this is the gate level netlist, and this is the VDC. So I'll just we'll just start PT shell. PT shell is exactly, I mean, in terms of the user interface and the most of the commands, PT and DC are same. So DC by default reads .synopsys DC setup. PT by default reads .synopsys PT setup. So if you want to put any default command, any default settings that you want prime time to load up right at the start, you can put all of this into the .synopsys PT setup. So we just invoke prime time here. The header tells us what all licenses are available. Prime time SI is for signal integrated analysis. Prime time PX is for power analysis. You can do report power and do all sorts of power analysis in prime time PX. Now, once again, the link library, the search path, these all are same. The only thing, so I'll set the search path and the link library first. And then see, there's no, although there is a variable called okay, There is no concept of target library in prime time because prime time is not a synthesis tool. So you just need to set the link library, which means that all the library cells that are present in your design must be mapped to one of the cells present in the one of the libraries in the link library. So we have set link library to memory and standard cell. In this case, there is no memory in our design, but doesn't matter. So I will read to read the netlist now. Prime time is not used for reading the RTL. It should be very clear. Design compiler reads RTL, does synthesis. Prime time works on netlist. So whenever you read in your design into prime time, it has to be a netlist. Or you can even read DDC. It supports reading of DDC. So once you read DDC, you'll get the constraints also. If you read, so let me read DDC first. So I'll read DDC example.gate.ddc. So any database you read into prime time has to be synthesized first in DC, right? So please don't confuse and try to read RTL inside prime time. It's no use. So I have read that. Just to make sure we check the current design example. And now I do a link. Now this link process will will tell us that whether all the cells inside this design are whether they are found in the library or not. So once it when we do link, it will load these DB files, and it gives some information that so many cells are unused in some library. This is all right. This is just some information sake. Obviously, we will be using a subset of all the cells that are present in the standard cell library. So it also sets up. So this is a very important. It is setting some default operating condition and default operating condition analysis mode. We will look into more detail in one of the lecture sessions about the analysis mode and operating condition. But just make a note that operating condition analysis mode is set to on-chip variation. This is very important for STM. We will see this in detail in the other lab and one of the sessions. So by default, what PT is doing, it is setting this, it is issuing this command: set operating conditions minus analysis type on-chip variations minus library this. So it is picking up some operating condition from. You could use a report design command to check the stuff. It will tell you that analysis type is on-chip variation. I'll give more detail on that later. Operating condition min name and max name are same because there's only one library we have read. It reads the operating condition from the library, which is the process is 0.99, temperature is 125, voltage is 0.95. It tells us what is the Y load model used. Y load model is area based, automatic area based selection. The tree type is best case. So now we are talking about tree layout. I haven't read any parasitic data. Parasitic data is read using this command, read parasitic. I'm not going to use that for this particular lab. We'll see this in the next lab. So now what we want to do is we want to see what type of constraints are. So DDC has both netlist and constraints. Now this DDC was written at the time of synthesis. So if we contain all the synthesis constraints, there are not much here. We can do a report timing and see, or we could do a report constraints minus all. We could do a report constraints minus all. So I do report constraint. So in fact, prime time by default. So if you issue any command for which prime time needs to, so we linked the design and that's all. We did not do anything beyond that. So you have to give a command called update timing, which is this command, to make prime time do delay calculation. If you do not give this command and the first command you give, which needs timing data, prime time will do a update timing implicitly. So here we see that as soon as I give report constraint minus verbose, prime time starts doing update timing. These messages are from update timing. So any constraint change that will force prime time to calculate timing again. Prime time will then run this command update timing by itself, and for this it was pretty quick. But for big designs, a delay calculation takes a lot of time, so you have to be careful when to. So you have to be careful while changing constraint for a big design and for a big chip, and you should be prepared to wait for that long, right? So let's say the chips I work on, the update timing usually takes somewhere around 3 to 4 hours easily. So we try to make sure that we only do update timing only after we are very sure that okay, all of the constraint changes have been ported in. So now here we see that report constraint is telling us that it is giving us the worst timing path. We can also report if there is any clock. There is no clock in the design, so the only constraint is a max delay. So we will say report constraint so the only constraint we have is the max delay constraint. What I can do, I can also write SDC synopsis design constraint file, and from the DDC we wrote out the SDC. Let's see what SDC contains. SDC will contain all the constraints that it's picking up from the DDC. So these are this is the SDC version. This command came from the default. This is the default operating condition command that prime time issues, and we see that this was the constraint that is coming from synthesis. Set max delay 2 from all input ports to all output ports, and then the while load model, which is so some of the commands we did not give during synthesis, but they are part of DDC because these are default cases like while load model and operating condition and units, so they are written in DDC. So we see that what are the constraints that I gave in synthesis. I gave a max delay constraint. Now what I'll do, I'll remove this constraint. I'll remove all the constraints, whatever. So a simple command to remove all the constraints is reset design. So this means that if I read Verilog netlist on one hand, and if I read DDC on the other hand and do a reset design, both are true. We have read in the design and we have removed the constraint. In one case there are no constraints in the first place. When we read DDC, constraints are part of DDC, but I have now cleaned up. I have cleaned up this design. Now let's do one thing. Let's try and report timing now. So we know that timing from A to F is not correct because A to F path is not true. It is a false path in the sense that there is no case where no functional case where the path exists from A to F, C to F, B to E and D to E. But prime time being a static timing analysis tool does not assume any value on F. So what I'll do, I'll try to report timing from A is a bus, to F and see what happens. So prime time again did update timing. It gives a message that no constraint path. That means prime time does not find any constraint path in the design. Obviously it will not find, we don't have any constraints here. Now there's a variable which I'll set timing report unconstrained paths true. Now by default this is set to false, and if this is set to false then prime time will not even report any unconstrained path. But we still want to see the unconstrained path, we want to see the path delay. Fine, constraint is not there, but there are two parts, delay calculation and timing constraint. Timing constraint is not there, but I still want to see the path delay. Now I set this variable to true and again do a report timing, and now I see a timing report. So without assuming any delay on S, any case on S, select pin, prime time will give me I haven't done anything now, and it will give me the timing report from A to F, right? So let's say let me show you some other applications of report timing. I want to report timing on all the F. So F is of total 4 bits to F. Now I want to see the worst path ending at F. So worst path ending at F starts from select. Now what I'll do, I want to see 10 worst paths, right? So I want to see the path ending at F and top 10 paths, top 10 in terms of order of decreasing path delay, right? So I do this and it gives me all 6 paths, right? It gave me number of paths. Now I want to see a path summary and not the full path, so I give minus path type summary. So it gave me that this is a summary report. Start point, end point, slack. Start point is select, end point is F, slack is infinity because path is unconstrained, right? If the path is constrained, it will report slack value here. So I gave maximum 10 paths, but it's reporting only 5. Okay, let me see. I can do minus from A. Okay, now see this. Now please note that let's consider F0 now. What I'll do specifically to F0. Now when I give max 10, max means that it is related to the endpoint. That means max, this max is a short form for max endpoints, maximum number of paths with unique endpoints. In this case, F0 is just one endpoint. So, and there are a number of start points. So there are paths from, there are timing paths from A to F, B to F, C to F, D to F, cell to F. But max path will report, it will count the number of paths in terms of unique endpoints. So in this case, let's say I give F star, there are 5 endpoints, F0, F1, F2, F3 and F4, and among all these start points it gave me the worst start point. So the max controls the endpoints, unique endpoints. Now I want to see that on F0, for example, on F0, so if I give F0 and max any number greater than 1 does not matter, because F0 is one single endpoint, right? One single endpoint, and it will give me, it will, from all these start points, it will choose the worst start point. So any number I give, it will just report one path. Any number I give, doesn't matter, because there's only one endpoint. Okay. Now I want to see multiple. What if I want to see all these start points here? I don't want to. I want all these start points that have paths to F0. The option is called n worst. So if I give n worst 5, now it will give me 5 paths. So this endpoint is fixed here. It will give me the top 5 worst paths from all the group of start points. In this case, all the worst 5 paths are from select. So what I'll do, I'll increase this number. I'll make this 10. Okay, still top 10 paths are from select. I'll increase this number to 50. And now I see this. Select to F, B to F, D to F. What about A? So there are so many paths from, I say 100. So if we see that there is B, there is cell, there is A, there is C. So now we see all the paths, right? So if you want to see, you use max path. If you want to see multiple, if you want to see the worst path to a particular endpoint, use max. And you want more than one endpoints in your timing report, use max path. However, if for a particular endpoint you want to see more than one start point, use the option n worst. Please read the manual of report timing and read about the max path and the n worst option. This is very, very important to understand how report timing works, right? So max path, it will, for a particular endpoint, it will choose the worst start point and show you. If you give n worst more than 1 for a particular endpoint, it will report, let's say if you choose say n worst 5, it will report 5 start points ending at this endpoint if those 5 start points exist. Now in this case, consider this. A is of 4 bits, B is of 4 bits, C is of 4 bits, D is of 4 bits, right? 16 plus 1 select 17, So each bit of F and E has 17 start points. So there will be minimum 17 start points, but we see that select has so many paths. Why? Because of a good amount of combination logic here. You will have rise path, you will have false path. For example, let me now report a detailed timing report and do just inverse 2. I want to see the worst 2 timing start points to F0. Now here we see that input external is 0 because it's default, we haven't done anything, path group is none. So now we see that select in is falling, it goes to U26Y, 28Y, 29, 23. So both timing reports look same, but there will be some difference. Let me just so here it's only reporting the output pins. So what I'll do, I'll make it report the input pins also. So here A3, A2, A5 and fall, rise. 26 A to Y, fall to rise, 26 A to Y, fall to rise, 28 A3 to Y, 28 A3 to Y, rise, 29 A2 to Y, 29 A2 to Y, rise fall, 23 A5 to Y, fall and fall. Both timing reports look same. Let me just expand it a bit. So it looks like it is reporting multiply for there should be some difference. What if I report nets and now it will report nets also. So this is where you can expand this, but so there will be a fall path. All these are fall paths. There will be also be a rise path somewhere in. If we do more, so there are so many paths from select. U to A to Y. So once you start doing more experiments with report timing, you'll understand that the paths there are subtle differences in terms of the transitions, in terms of the which pin the timing path is going through. So in the earlier case, we saw that the timing report was same for all the paths, but when we do unique pins, now when we do unique pins, time will report it for the paths, 2 paths. Let's say if then all the pins are same, it will not report the other path. So unique pins, it will unify the data for you. So now in this case, let's see this. Let's see the last 2 timing reports. For the last timing report, the path goes through U23A4. For this one, path goes through U23A3. So these 2 paths are different. Although the delay is same, but the path is different. And when it goes to post layout, they will become still more different depending on what is the load on each of the pins, what is the routing, and so on. You could still expand. You could still expand the significant digit number. You could make it to 3, and then it will expand it for you, right? So this is the way you work with report timing. You have many options still. You can choose through points and so on, right? But important point now, we saw here that prime time is reporting paths between A and F, C and F, D and E, and D and E. Now we do not want that. Now let's say this is part of a bigger design and we want to root out all the false paths like this. So first we'll try out a command called set case analysis. So what we will do now, we will try and report timing for both the cases individually. For the first case where select is 0, for select is 0, F will be disabled. There will be paths from A and C. So the path will be from A and C to E. F will be 0, and obviously B and D will be blocked. So what we will do, we will set case analysis 0 on get quotes cell. Since we have changed the constraint, we do update timing, and prime time will give the message because it calculates update timing. You can do a report case analysis to tell us what is the case analysis we set. So we have set select to be 0, and now we report timing on F. Report timing -2 F, and we see that nothing. There is nothing. Since F any so this is the AND gate. So this is the AND gate controlling F. If we set S to 0, this AND gate is disabled automatically. Why? Because in AND gate the functionality says that if one pin is 0, the output is 0. Now prime time, although it's not synthesis tool, but it understands the functionality because it reads the dot lib. So it read in the dot lib, it knows the functionality of AND gate, and it shows us that there is no pin, internal pin or net feeding to F0. It starts with F0 and ends with F0. That's it. What about E? So E, we see there's a path from A, which is what we expect. So what we'll do, we'll say path type summary, and we'll do a max path 5 and inverse of 5. You see a lot many paths. So okay, inverse is 5 is my okay. We will increase this to let's say 20. Only E. Just like this goes. Okay, so we'll still increase the inverse to C. So there are all the paths looks like from A. There should be paths from C. Okay, we see the path from A and C. So we see that okay, there are at any pin, any E pin. In this case, it's E3. There are paths from both A and C, but you can try. Now let's see what happens to the path from. We saw that okay, F is disabled. There is no path to F. We'll try and report path from B. I give star because B is a bus. Now we see that path starts from B0. It goes to some cell, but now it stops. So it would have happened somewhere here. So now this mux might not be. It's not represented as a mux in the gate level network. It's a logical description. So looks like design compiler picked an A022 cell, and B is going to the A022 cell, and the path is stopping here, which is expected because setting select to 0 would disable this path. Again, it would be same with D, I guess. It is same with D. So in the netlist, a mux is represented by a group of combinational cells, right? So now I want to see the other case. I want to set the case analysis to 1. I do update timing, and I will report timing from B, and I see that B is going to F, which is good. I'll do a report timing from D. D is going to F, which is good. I'll try and report timing to E, but there is no time. There is no path from E because start point is E, end point is E, so there is no path to E. E is disabled. Again, I check from A and from B, from C, both are same. They go to AO cell and stop there. They don't go to the output. So case analysis is a very nice way to analyze timing in 2 different modes by selecting some value on the selector. Now what about the selector? We have set the selector to 0 in one case and 1 to one case, and we try to report timing from cell. There is no time. There is no timing from cell because cell is now fixed value. static timing analysis by default will assume no value on any pin. Once you set the value on any pin or a port, the timing through that and from that would be false. Why? Because that pin is set to a particular value. It does not change, right? So this is how you use set case analysis. Now what I'll do, I'll show you a second way of doing things, which is using false path. In this particular example, the disadvantage of setting case is that you need to do update timing after changing the value on set case analysis. In a single session with the case analysis, in particular example, you cannot see all the paths, that is A C to E and B D to F. So what I'll do a reset design again. It will remove all the constraints. And now what I'll do is I use false paths. Now I know that path from A to F is false, C to F is false, B to E is false, and D to F is false. D to E is false. So I'll set appropriate case analysis and appropriate false path command. I'll say set false path minus from get ports A, all A, minus to get ports F. This is one false path command, A to F. Second, I do C to F. Third, I do B to E. Fourth, I do D to E. Right. So, and I do update timing. So it will do update. It will give some messages. Okay. Now I can see what exceptions I have placed by report exceptions command. So report exceptions tells me that there is a false path from A to F, C to F, B to E, and D to E. It tells us whether the path is false for setup or hold. It is, since we did not give minus setup minus hold, it is assuming the path is false for both, right? So report exceptions is one way of telling us what exceptions are applied. Now let's do a report timing minus 2, let's say F0 and a very big inverse number of 50, let's say, and I do a path type summary and see that the path is from cell B and D. You cannot find a path from if I try to report timing minus from A, let's say minus to F. So in this case, it is reporting this path A to F, but in this, see what false path will do, if you remember from the lecture session, false path will remove any timing constraint on the false path. And there was no timing constraint in the first place in this case. Why? Because there is no clock, there is no max delay. What I can do is I can set max delay again, just to make it interesting, minus from all inputs to all outputs. So we see that the paths were unconstrained in the first place, right? A to F is already unconstrained, and you applied a false path, so it did not actually do anything. Case analysis, on the other hand, it allowed prime time to do some logic analysis and switch off those paths, right? But false path is like telling prime time, okay, please do delay calculation, but don't do any checking. And it was happening in the first place. The same thing was happening in the first place. There was no constraint, so prime time did not actually do anything. So what we will do, we set a max delay constraint, whatever was used for synthesis. False path is already in place. We do update timing, and now we report timing from A to F. Now the path is unconstrained, which is okay, but path from, what happened to path from B to F? Path from B to F is not unconstrained, it is constrained path, because we applied a max delay of 2. Path starts from B, ends at F, data arrival time is 0.62, max delay constraint is 2. So it calculated the slack. And now if you do a path type summary, it will also give slack. This will also give slack, right? So false path is when you have a constrained path and it is violating or it is not true even if it's met, you can use false path, right? So I hope the distinction is clear between false path and case analysis. I'll do a reset design again, and now I will tell you detail about how to use virtual clocks in this case and why virtual clocks are good, right? Now let's do one thing which we could have done for synthesis also. Now what I know from this design is that path from A to E, this particular path from A to E and C to E, I say they both belong to, let's say I have assumed that they will belong to a clock domain called CLK1, right? CLK1, and B to F and D to F belong to a clock domain called CLK2. So I'll define two virtual clocks. The reason will become very clear why. So let me define two virtual clocks. So I set create clock minus period, any period I can give it the virtual clock. So I'll just give a period 10 and I give a name CLK1. Now I again create a clock called CLK2. So I create two virtual clocks. Now what I do is that how do I associate a clock with a port? I define an input delay. So what I'll do, I'll define an input delay of 0 minus clock CLK1, and I do this for the ports. So this is how you give a list of ports: A star, C star, because we said that A and C and E belong to same. So I'll set input delay on A and C using clock 1, input delay 0, and I using clock 2 on B and B. So A and C belong to the clock domain clock 1, B and D belong to the clock domain clock 2. Then what I do is I set I'll set appropriate output delays. So I'll set output delay. Now I'll set a very tight value. I want to see some violations. In this case, I see that the paths are usually in the range of 0.3 to 0.6. So what I'll do is let me set the output delay to be 10 itself. Minus clock 1 get port. This is just because I want to see some violations. I want to make things a little bit clear. List now output port. I will. So I said that A, C, and E belong to clock 1. So there will be, we'll give E here, and I'll give on clock 2. I'll give the port F, and I'll do update timing. So now let's report timing. Now we have defined a clock 1, and on it we have defined input delay for A, C, and output delay for E. Similarly, B, D, and F belong to the clock domain clock 2. I haven't done anything else. I'll do report timing. Now see, so first of all, it will report. It will have two path groups now, CLK1 and CLK2. CLK1, E is associated with CLK1, F is associated with CLK2. So let's see the first path. First path starts from input external delay 0. That's how we define. Path starts to cell. It goes through combination logic. Data arrival time is 0.66. Clock 1 rise edge setup. It's a setup check. The rise edge would be 1 period apart. The capture edge, so it's at 10. Output external delay is 10. So in what it means is that we did not leave any time for the combination delay. The input delay is 0, output delay is 10, the clock period is 10. So there is nothing left for the combination delay. So whatever is the path delay here, it will violate by the same amount. There is no sequential element involved here. So there is no setup margin. So path delay is 0.66, slack is 0.66. Good. Clock group. Path group is clock 1, path group clock 2, cell, and again path delay is 0.67, it violates by 0.67. Now let's see some interesting timing report, where we will see, we'll now report timing from, now let's try to report the timing from A to F and see what happens. Now we see that launch is by clock 1, which is okay by because A has input delay with respect to clock 1. The capture is on clock 2. Why? Because F is on clock 2 and we gave report timing from A to F. So again input external delay is 0, output external delay is 10 and the violation is Z. So now we see that path is getting reported from, we can also try B to E. Again we see the path is from B to E, which is fine. This is what we expected. So we just created clocks, and by virtual clock we could constrain it. So if we, let's say, keep the input delay to be 0 and make the output delay 9, so it will give 1 nanosecond for the combination. We can use this particular constraint for synthesis also. But now it becomes clear that A is on clock 1, C is on clock 1, B is on clock 2. So A to F is false, we know that. So now if you apply a false path here, you will see that you can apply a false path here and you will not see. Now in this case all the paths are constrained, so what I'll do, I'll apply this false path from A to F and I'll report time from A to F now. It will do update timing implicitly. So it will do some update timing, and now A to F is unconstrained. In the first place it was constrained A to F, I constrained this path, and now I am setting a false path. So now it shows me that A to F is unconstrained, although it reports the path delay, but tells me that path is unconstrained. Why? Because I have set a false path. I'll remove the false. So this is the way you can use false path for constrained path. If the path is already unconstrained, false path is not of any use, right? I'll do a reset path. Reset path will remove any constraint from whatever option I give. So I use the same options and I just report again to make sure that it is gone. So okay. Now what I'll do a more sophisticated analysis. What I'll do, I'll set false path minus from get clock. So the advantage of creating two domains here is that I can now do a false path between the clocks. So this command tells prime time that any path launching from clock 1 and capturing at clock 2 is false. What are these kind of paths? These are clock 1 launch A and C, clock 2 capture is F. So A and C to F is a false path. This is what we are doing in one single command. And we need to do the other way around also, B and D to E. So this is what we do. From clock 2 to clock 1 is false. Now let's try and report timing from A to E. Path is unconstrained. B to E, path is unconstrained, right? What about, we need to make sure that whatever accurate paths, whatever real true paths are there are getting reported. So we try and report B to F, we are good. So earlier we had to give false paths for each set of inputs, to each set of corresponding outputs. We had to give 4 set false path commands, and let's say if your design, you want to expand your design, you have multiple cases like this, then you need to add so many other false paths, right? But in case of virtual clocks, what we have to do is just give 2 false paths from one clock domain to other clock domain, and this can easily scale up. Let's say you add more inputs here. The number of inputs you add, number of similar functionality you add, you can again segregate this into virtual clock domains. This application of false path also applies to designs who have real clocks and multiple clocks. If you have real and multiple clocks, if they are asynchronous, you need to specify false path or use a set clock group command. Whatever, both are fine. So this was the focus of this particular part of the lab, to get you acquainted with the exceptions. So we saw case analysis, use of case analysis, use of false paths, use of virtual clocks and again false paths to declare asynchronous paths between two clocks. What I'll do is now I'll show you an example of a disabled timing, but it's disabled timing is comparatively less used when it goes to when we compare it against false paths and multi-cycle paths. I do not have an example of multi-cycle paths. So let's first try and analyze what is the fan out of selecting report. So what I'll do is all there is a command called transitive fan out. Minus from get ports cell. So this tells me what is the fan out of select. So select goes to so many places. Why? Because it is expected. Why? Because select goes to these two mux objects. It goes to this here and here and so on. Let's see from A0 how many places it goes. Okay, A0 goes to so these are different labels of. So A0 goes to U28. From U28 it fans out. So A0 goes to, so any timing we do through report timing, let's do a report timing minus from A0. We can also know it from the timing report. How? Let's see. So report timing from A0 tells us this. We can expand it. We can do a minus. If you want to see the transition in capacitance, you can do it. The transition in capacitance again. So we see transition in capacitance, and if we do nets, we can also see a fan out. Now we see this is the fan out. Now this is very interesting. So this tells me that A0 port goes to A0 net, and the fan out is just one. So A0 goes to only this cell. We will also expand this a bit further by doing input pins. So this is a more descriptive report. A0 goes to one cell. It goes to the A4 pin of U28. It goes to A2, and again further the fan out. This fan out is 3. This fan out is 3, and so on. Now let's say for some reason I do not want any path through A0. Any path. For me, let's say now the designer comes to me and says that the 0th bit of A is always grounded for me. I do not use this ever. So one option is to set case 0 on A0, which is good. Second thing you could do is you can set disabled timing. Set disabled timing. Now set disabled timing. The syntax is like this. Slightly different from other commands. Set disabled timing. We give minus from the pin name. So here I give the pin name A4, and so I want to disable timing from A4 to Y. So A4 minus to Y, and of which cell? Of this particular cell, which is U28. Now I will try and report timing from AB, and there is, so it goes to A4, U28, A4, and stops here. Why? Because path from A4 to Y is disabled. Now this has one more consequence. What happens is that now so A022X1 is a, let's open the netlist and look at the cell. Example.gate.c. We'll open this. We'll go to U28. U28 is this one. It has 3 pins. So it has 4 input pins: A1, A2, A3, and A4, and 1 output pin Y. A0 is going to A4 as we saw. Now this is has 4 inputs. So what prime time will do in doing transition calculation, in default case when no exception is applied, the transition on N5 will depend on the worst case transition among all the 4 input pins. So prime time will only keep 2 values here: rise transition and fall transition for max and min case. So there are total 4 values. But if you remember, Y's transition depends on the transition on the load on Y and transition on all A1, A2, A3, and A4. But prime time will not keep individual values for A1, A2, A3, and A4 for calculation of Y. It will keep the worst transition value at Y. Worst depends on what is the worst transition among all the 4 pins: A1, A2, A3, and A4.
Now if you do false path through A0, this does not change the transition at Y. But if you do a disabled timing, this changes transition at Y. Why? Because for any disabled arc, prime time will not use it for timing calculation. In this case, we disabled the timing arc from A4 to Y. It means that now A4 is out of question. Prime time will use the worst value among A1, A2 and A3. So this is the difference between false path and disabled timing. Disabled timing affects delay calculation. False path does not affect delay calculation. False path only affects the timing checking, the constraint checking, the slack calculation. Disabled timing affects a lot more. Disabled timing affects the delay calculation itself. So you need to carefully understand the difference between disabled timing and false path from this point of view. So use disabled timing. So in that sense, disabled timing is much more dangerous. Saying set false path from A0 and saying set disabled timing in the way we applied from A4 to Y of this particular cell. In both these cases, the delay calculation changes. So that's why disabled timing is a very, very dangerous command. So please use it carefully, and before that, first try and understand very clearly the difference between these false path and disabled timing. Right? Okay. This was. Now let's. I'll exit prime time now. For any command, any output you can. Okay, let me show you a couple of commands. For any command, if you want to report you want to store this output, you can store it in by doing the output redirection. You can store it in some file. You can open up temp.rpt and see that it's there. Then there's one command called report analysis coverage. Report analysis coverage will let us just give this and see what happens. So report analysis coverage will give us a summary of the type of check, total number of checks that are present in the design of such nature, how many are well met, how many are violated, how many are untested. So this gives a very nice summary of your design, how many checks are there. In this case, there are only two types of checks: output setup and output hold. This out setup means the checking is done at the output via output delay. So there is an out setup check means setup check for output delay. Out hold means setup hold check for output delay. There are total 10. Why there are 10? 5 pins of E and 5 pins of F, total 10. So there are 10 places where setup and hold is checked. All setup is violated, all hold is met. How many are untested? 0. So this, if you have a lot of untested here, you need to be very, very sure about it. What is untested and why is it untested? So this gives a very good measure of what all checks are being done in your session and how many are tested, how many are met, how many are failed. Let's look at one timing report of hold also. So I'll just review what I did in design compiler also. When I do a report timing, by default it will give me the worst violating path in each path group. Here it gives me 2 paths because there are 2 path groups. First is clock 1, second is clock 2. It by default path type is match, that means the setup check. How do you know it's a setup check? Because launch is at 0, capture is at 10. They are 1 clock period apart, it's a setup check. If I want to report hold, I do a delay min. Again it gives me 2 reports, one for each clock group. Path group clock 1, path type min means the hold report. The launch and capture edges are same, exactly same. We'll worry about this output external later, don't worry about the negative value. I'll talk about this later in the other lab. So this is the whole timing report, and please make sure that you understand the difference between setup report and whole timing report in terms of launch and capture edges, right? Okay, we all know what is the report what is the command to report clock. Same command like report port works here also. We do a report port minus verbose, and it will tell us at each port what is the output delay, what is the input transition, what is the input delay, and so on. So it gives us detail about all this. Now, when you are working on a big design or a big chip, you have applied, you have read in the netlist, you have applied the constraints, you have done update timing, and you are doing some analysis. Now you want to continue this work the next day, but you want to quit prime time, and you know that your update timing takes few hours, right? So you don't want to again come back tomorrow, do everything, wait for few hours, right? So you can save a session. So I can save there's a command called save session. So I can save a session, and I have to just give. So it has an option of including noise data also. In this case, we are not worried about the noise data, and it can also save libraries. But at this point of time, I don't want to save library because library is not changing for me. So if the library is not changing for me, I can choose not to write out the library to reduce the. So this file can be pretty big. The session file can be pretty big. So you need to make sure, you need to be very sure about what data you want to save. So in my case, I just want to save the timing data. So what I'll do, I do a save session, and I give a name called my session. It will save netlist information, environmental conditions, timing information, and all those. Right now, I exit it. I again open prime time. And now I can do a restore session on my session. It will and now update timing is already done because it saved all the data, right? So it does not need to calculate the timing values again. Now I can simply go ahead and do a report timing without any delay, right? So obviously it is not apparent in such a small test case, but when you have a big design and a big chip you are working on, this functionality is very useful. We make use of it all the time, right? You save the session, so you can even save the session and point out to some other engineer who can load the session. So on a big chip at one time on full chip SCA, there are more than one people working, right? So all of them, you can save a session, you can give it to another engineer, and he can use that, restore that, and do analysis himself, right? So this was about the lab 1 where we concentrated on the timing acceptance. I'm assuming that you still remember your create clock concepts from design compiler. They remain same in time. In the next lab, we will look at how to do post layout timing analysis, which is very important, right? Which is the most important thing of the STA. So we'll look at how do we read the post layout netlist, how do we read the parasitics, what checks do we do. So we did lab 1 of design compiler. We had a design. We'll use the same design, but now in this case it will be a post layout netlist, and we'll also use the parasitics, right? Thank you.